Okay, I knew something wasn't gelling right on that problem 12. I screwed it up. We got the right numbers, okay, but when I was going, wait, the net force should be zero when I was first looking at it, but then I thought when I saw the solutions that they had a number there. No, they had a zero there. Okay, so let's take a look real quick, right? Um, Without drawing out, well, I'll go ahead and draw the pictures again. All right, so what is the network? Here's our situation. All right, so we got it. It's going up a hill. We got a distance d that's parallel to the static frictional force pushing it up. Gravity is doing work here. Why? Because gravity is at an angle, and so you've got the mg sine function. You've got the mg sine portion of the here. Let's just draw the picture. Okay, so. I think you can see this, all right? I think this shows up on the screen. Everything is on the screen. It's getting recorded, all right? You don't need my mug up here, but I should probably turn that off. But here we go. So once again, and any angle will do. And we have a package being pushed up. Well, it's on the back of a truck, and it's not sliding backwards. So there's the static frictional force is going. I screwed that up, all right? Usually the static frictional force does no work either because especially if it's because nothing moves, all right? So this is an interesting problem. But anyway, so we've got mg going down this way, and we've got the normal force going up this way, all right? There we go. All right, so here we go. Let's look at the forces in the and let's break mg down into its two components. Let's make this flat. Static frictional force going that way. Mg sine theta going this way. Normal force going up this way. And mg cosine theta going this way. All right. Okay. So what's the net work done on the package? The net work, it's just like when I lift up, when you lift something up over your head, the net work that's done is you're doing a force times distance going this way, but gravity is doing a force times distance going the opposite way. And so the net force is equal to zero. All right, so the net work done, or the net work is equal to zero. All right, because work done by gravity, and what they mean is this component of gravity, the work done by gravity, would be mg sine of theta times the distance, but that's negative. Okay, well, what's the work done? If it's going to displace like this, it's going to displace over here, then what's the work? And here's our distance. Okay, then that's negative. So what's the work done by the normal force? Work done by the normal force is perpendicular, so that's equal to zero. All right, pretty straightforward. Can't believe I went around the bend on this one. And then what's the work done by the static frictional force? Work done by the static frictional force is the static frictional force, F of S, times that distance, which you can get from there. I mean, you could get it from this, because the sum of the forces in the x direction, once we, for this guy, sum of the forces in the x direction are equal to zero. Why? Velocity is constant. No acceleration. Okay? And so I've got minus mg sine theta plus f of k. So f of k, or, man, I'm so used to writing that. F of s, the static frictional force, is equal to mg sine theta. Okay? All right. All right. Okay. There we go. That'll do. That's much better. All right, and I'll send this correction now.